We're going to be defining something called electric flux. Flux itself could be a word you're familiar with. According to the dictionary, it's the rate of transfer of fluid or particles or energy across a given surface. So it's the transfer of something through something. We're going to talk about electric field lines through a surface, in particular a Gaussian surface.
Just before we get into our definition of electric flux, I want to illustrate how the angle is going to be important here. So what I have here are some arrows on my blackboard. They represent the electric field, and I have here a surface. It's a roll of masking tape. If I hold up my roll of masking tape like this, we see that we get two lines cutting through my surface. So when my roll of tape is up like this and my lines are like this, we get lots of lines cutting through. There's a lot of flux. If I tilt my roll of masking tape, now I only have one line cutting through. So I've rotated a bit. There's only one line cutting through. If I rotate it even more and it lies like this in the plane, now there are no lines cutting through. So as we get into the idea of flux, we're going to see that the direction of the field and the loop matters.
This feels like a good time to write down our definition of electric flux. Electric flux is a scalar quantity, and that scalar quantity represents the number of electric field lines penetrating a surface. Electric flux has a symbol of the Greek letter phi. So again, here's a downfall of physics. Lots of different things use the same symbol. We used phi as phase constant in our wave sections, and now phi is back again and it stands for electric flux. I'll put an E on it to remind us that we're talking about electric flux. Later on in the class, we'll talk about magnetic flux too. The units of electric flux are newtons times meters squared per coulomb. So this idea that it's a scalar quantity, I just want to elaborate on this a tiny bit because I think your book is actually a little bit ambiguous. As we went through the process, I held up my loop of tape here and we saw the lines going through it. There's actually two directions the line could have gone through it. So the lines could go through it this way, or if our electric field was in the opposite direction, the lines could go through another way. The direction of the electric field matters. It matters if the lines go in or out. For example, when we did our what's in the box questions, the lines going out meant there was a positive charge inside, and the lines going in meant there was a negative charge inside. So it's not that direction doesn't matter, but our phi, our electric flux, it is a scalar. It does not have direction. So flux doesn't go in or out. Flux is just a number. A positive number means electric field lines go out, and a negative number means electric field lines go in. So make sure you're aware of that and you don't write down electric flux as a vector quantity because it is not a vector. Let's start to get our idea now of our equation for electric flux. We know that if the electric flux is the number of electric field lines cutting through a surface, then the area of the surface matters. So on the left here, we just have a square. In my physical demonstration, I used a roll of masking tape. So the area of this square matters. If we have a big square, we'll get more lines. If we have a small square, we'll have fewer lines. So let's get the dimensions of well, maybe it's a rectangle rather than a square. So let's say it's got a dimension of L along the top and a dimension of W for width along the vertical. So the area of our rectangle would be length times width. And in this picture, all of the electric field lines cut through the surface. Now in my masking tape demo, I showed that the angle matters. So what if we take this rectangle and we just tilt it backwards, same way I tilted my roll of tape? So now here's my rectangle, except it's tilted. So my rectangle still has a length L, and it still has a width W, but this time fewer lines cut through. And in fact, what we see is that this vertical bit, and I'll draw a 2D picture on the next slide that might help, the number of lines that cut through this slanted bit would be the same number of lines that would cut through this perpendicular projection, this perpendicular part. Okay, let's get that written down, and then we'll draw the 2D projection on the next slide. So now this time, the number of lines through the tilted surface, that tilted surface has the same total area as our vertical surface. The tilted surface is the same as the number of lines through the perpendicular surface, or through the surface which is perpendicular to the field. And we would say that that surface that's perpendicular to the field, so this is the part of this surface that's perpendicular, this will have an area that we'll call A perpendicular. Now, of course, we'd like to know what is A perpendicular and how are we going to use this to find the electric flux. So now here are my two surfaces, here with the upright rectangle and here with the tilted rectangle. And what I have are just side views because sometimes it's easier to see with a side view. So when it's upright, then my surface is perpendicular to those electric field lines. When we tilt it, it's tilted. So let's make sure we've got our dimensions. The length is L and the width is W. My length L in this picture now is coming in and out of the page. I can't easily label that, so I won't bother, but the width is still W. And the area of this rectangle is length times W. So here's the picture. This is the picture where all of the field lines cut through. Okay, what happens when we tilt it? Well, now our rectangle still has a width W, but we have fewer lines, and the number of lines that cut through are however many lines that cut through this perpendicular part. Okay, so this is perpendicular to the field. It's like a component of this part of the line. So it's the perpendicular component or the perpendicular projection, some different ways you could say it. So I'm going to call this W perpendicular. It's going to be at an angle theta to W. And up here in our top picture, it still has length L and it still has width W. Okay, so now in our picture, the number of lines that cut through this surface is the same as the number of lines that cut through this perpendicular surface. So the perpendicular area, that's the part we care about because that's the part that the lines are cutting through, is the length, that bit didn't change, times W perpendicular. We see that W perpendicular is adjacent to our angle, so we can use cosine. So we can write L times W times cosine theta. Well, L times W, that's just the area A. So that's A times cosine theta. Okay, we're ready now to get going with our equation. Our electric flux phi, it depends on how big the electric field is, so it depends on E, and it depends on that perpendicular area. So let's fill that part in. So it's equal to E times the area times the cosine of theta. Theta is really important. You've got to get this one right. Theta is the angle between the electric field vector and the area vector. Okay, that might be a new idea to you. You're used to electric field being a vector, but area, how is that a vector? We're going to come back around to that guy. Let's just finish up with something. If you've done Math 2050, you might recognize this right off the bat as a scalar product. So electric flux is the scalar product between electric field and area. This gives you the quantity of how many electric field lines cut through the surface. Scalar product. Here's where if you're shaky on scalar product or dot product, you might want to go back and review. It's written, so we want the scalar products of two vectors A and B. We would write A dot B. That dot matters. You do have to put the dot in. There's two ways to calculate it. You can do magnitude of A times magnitude of B times the cosine of the angle between them. So it's always that angle in between A and B. Or you can multiply the x components, multiply the y's, multiply the z's, and add them up. So those are two ways to calculate the scalar product or the dot product. When you're doing a dot product of unit vectors, I dot I, j dot j, and k dot k, those are all equal to 1 because they're parallel and they have length 1. I dot j, j dot k, and I dot k, those are all equal to 0 because they're all perpendicular. If you need to review, there is a scalar product under the review section on Brightspace, and of course you can reach out to me with any questions. Okay, so we've got our equation for electric flux. I'll just mention at this point that this form, E dot A, the scalar product of electric field and area, it applies to cases when we have a constant electric field and areas that aren't weird. We'll get to weird cases in a minute or two. So now this question, area is a vector. This might be a new concept to you. So the answer to that question is yes, it surely is. So the area vector A is parallel to what we call the normal vector. And the normal vector is usually a lowercase n with a little hat on it. That's a unit vector. The direction is perpendicular to the surface. And if it's a closed surface, then it's outward from the closed surface. If it's not closed, you can't tell which way is out. So I have three surfaces drawn here. Let's draw the normal vector and the area vector. So our first one is just a flat plane. So the normal vector, it would either be up or down. I'm just going to pick up kind of randomly. So my normal vector would be up, which means my area vector would be parallel to that. My area vector will have units of meters squared. So area vector has direction of n units of meters squared. Whoops, I wrote a cubed even though I said squared. And the value would be the area of the surface, you know, for a rectangle, length times width, circle, pi r squared, and all that stuff. Okay, so that's one case, just a plane in our situation. What about if we had something like a cylinder? Well, if we look at the top of the cylinder, our area vector, or our normal vector first, would stick straight outwards because it's closed and it would be perpendicular. So our area vector then would be parallel to that and point straight up. Okay, likewise on the bottom, if we imagined we could see all that bottom surface, the normal vector would point down and the area vector would be parallel to that. What about on the sides of the cylinder? Well, on the sides of the cylinder, the normal vector would still be perpendicular. So on the right side, it would point out to the right. On the front side, it would point out at us. On the left side, it would point out to the left. So we could draw our area vectors in there. Okay, hopefully you're getting the idea now about what an area vector looks like. What about on a cube? Because we will do some things with cubes. So let's put in our normal vectors first. So on the top, our normal vector will come straight up. On the right side, it will come straight out to the right. On the bottom, let's just shade in that bottom. On the bottom, it will come straight down. Remember, we come out of a closed surface. On the front, it comes straight out. And on the left side, it will come out of the left. And then our area vectors are going to be parallel to those normal vectors. If you were doing this in a problem, you wouldn't have to draw the normal vectors. By all means, if it helps you, you certainly may draw them, but you don't have to draw them. It's okay to jump straight to drawing the area vectors. So this is what our area vectors will look like. Okay, so those are our area vectors. Next, it's important to make sure you know how to find the angles. So let's throw some electric fields on here and let's make sure we can identify the correct angles. So let's put in some electric fields and see if we can identify what would be the angle. I'm going to put in an electric field that's up and to the right. So let's say our electric field vector is all throughout space and it looks something like this. This is a situation you might have. So the electric field vector points up and right. The area vector points up. Theta is the angle between E and A. It's really important to get that right. Sometimes you're going to be given that angle, sometimes you're not. The angle between E and A would be this angle right here, theta. Okay, if you were given the angle between the electric field and the surface, that would not be correct. So here's your angle in this case. For our cylinder surface, let's draw an electric field that points towards the right. I like this example because it shows how the angle can be different depending on what part of the cylinder you're talking about. Let's look at the top part first. At the very top, the angle between the electric field vector and the area is 90 degrees. It's perpendicular. The electric field is to the right, the area is up, so the angle between those two things is 90 degrees. When we get to the side, the area vector is to the right, the electric field vector is to the right, the angle is 0 degrees. When we get to the front, the area vector is out towards us in the positive z direction, you might think. The electric field is to the right, the positive x direction. Those angles are perpendicular. And then the bottom is like the top, and the angle between the electric field and the area on the bottom is again 90 degrees. For our cube, let's say that we have an electric field that points straight down everywhere. Let's find our angles in each of these cases. So there's our electric field this time. Okay, so for our angles, let's start on the right face. Over here on the right, the electric field is down, the area is to the right. The angle between those two guys is 90 degrees. On the top, area is up, electric field is down. The angle between those two vectors is 180 degrees. Then let's go to the bottom. Area is down, electric field is down. The angle between those two is 0 degrees. On the front of the box, area is out, electric field is down. The angle is 90. And on the left face of the box, area is left, electric field is down. The angle is 90 degrees. Diagrams are often getting a bit messy, but hopefully now it's clear what you have to do to find the angle between the area and electric field vectors. So now we've pretty well gone through the process of what to do if your area is flat, if your surface is flat, and it's easy to identify the angle between the electric field vector and the area vector. But what if your surface wasn't flat, or what if your electric field wasn't constant? What would you do then? So what we could do is we could pick one tiny bit of our surface and we could find the electric flux through that surface. We could make it small enough so that it looked like a rectangle and the electric field through that little bit of surface was constant. So we could find that little area, we could find that particular electric field, we could identify the angle, and we could find the bit of flux through that little bit. Then we could go to the next little bit over, we could find the flux through that bit. Then we could go to the next little bit and find the flux through that bit. Then the next bit, find the flux there. Then we could go to the next bit, find the flux there. Then if we added up all those little bits of flux, we would have the total flux. Okay, so that's the idea of what to do if your electric field is not uniform or if your area is strange. So you would find the net flux by adding each small bit. And you might already have an idea of where I'm going with this if I'm talking about adding up a bunch of small pieces. So by adding each small, I'll underline small because it has to be small, bit of flux. So if it's only a small bit of flux, we would call that small bit d phi. Remember, the d is not independent of the phi. It means a small element of electric flux. And that each little bit of flux would be for each small bit of area. And that small bit of area would be represented by A for area and then a D in front of it to imply that it's a small bit. We would get our net flux by doing the sum. Doing the sum of a bunch of small things means adding up by doing the integral. So d phi, and then we remember that d phi would be the flux through a small bit. So that would be the electric field dotted with the area of the small bit. So now this expression is the general form for calculating electric flux. And you would use this in the case of having a variable electric field or a weird area. And I know I keep saying weird and it's not a mathematically concise term, but hopefully you're getting the idea. So if electric field is constant and A is a rectangle or a cylinder or a sphere or something like that, you just do E dot A. If your electric field is a variable or your A is an odd, not easy to calculate shape, you do your integral.